Hi, my name is Sergio and I'm going to talk about the BCD Counter mod24. Here I have the specifications. I'm going to do a down counter mod24. Here I have the inputs, the outputs and the TC24. This is a mini truth table of how this component works. So the input is going to be a 50 MHz clock signal, but I'm going to convert this in a 250 clock signal using a CLK generator that is going to be explained in the annexes. So now here we can see the timing diagram. Here I have the clock, the clear direct and the counting enable. When the counting enable is 1, and the counter goes counting, no? In this case down counting 23, 22, 21, and when it arrives to 0, 0, 0 in the tens and 0 in the units, the TC24 flag goes up and goes 1, okay? So now in the planning, here we can see the folder where all my files are. Here I have the 4 files that I'm going to use because it's a hierarchical structure, and then I'm going to integrate the CLK generator files. Okay, so in Quartus Prime I'm going to generate the RTL view, the test bench, and then in Model Sim I'm going to generate the functional simulation and the gate level simulation to see all the delays. Here we can see the internal structure of the counter mod24. As I said before, it's a hierarchical structure, so I have here the counter modulus 16, quadmux 2, quadmux 4, and here we have the CLK generator. This is the signal created by the CLK generator that goes inside of these chips, okay? And now here I have the logic components. So with these logic components I'm going to truncate this counter modulus 16 to obtain a counter modulus 24 by truncating, okay? So now it's time to do the truth table of the logic components, and thanks to this truth table I can obtain these equations of here and these equations of here that are going to be used to do that, no? The truncation. So now I'm going to the development. I'm going to translate the previous design into VHDL. I'm going to synthesize in Quartus Prime to obtain the RTL view and the technology view. Okay, so now let's have a look here in the code. Okay, so here I have the entity, the counter mod24, and all the components, no? Because it's a hierarchical structure, I have the CLK generator, the counter mod 16, the quadmux 2, and the quadmux 4. So now here I have the connections between the chips, chip 1, chip 2, chip 3, and at the end here I have all the equation and logic gates that are the same as the equations that I have seen before, okay? So it's a simple translation. Now in Quartus Prime I have generated this, no? I synthesize all, and I have generated the RTL view. So as we can see, this design is the same as this. So, yeah, we can see that all is well connected and all the files are okay. So let's have a look here at the CLK generator. As I said before, I'm going to explain later. I have the CLK generator connected to these signals, and that's it. So the technology view has this shape, and here we can see the number of data flip-flops that I have in this circuit, okay? Now it's time to do a functional simulation in Model Sim. Let's have a look on it. Here we have the simulation in Model Sim. As we can see here, we have the clock, the input clock of 50 MHz, and then we can see here the signal created thanks to CLK generator. It's a signal of 250 MHz, sorry. And here I have the clear direct in 0 and the count enable in 1. So because it's 1, it goes counting, goes down counting 22, 23, 22, 21, and goes down counting. And when it arrives to 0, 0, as I said before, the TC24 goes 1, okay? and when it's 0, 0, it goes 23 another time, and goes counting every time. So now let's have a look on gate level simulation. Thanks to this simulation, we can see the delays, no? So here I have the rising edge of the CLK 250 Hz. From here to the output, I have a delay of 6.5 nanoseconds. So it's well. In the timing analyzer in Quartus Prime, I obtained here all the delays, and I can obtain the maximum frequencies of operation with this, no? With this formula. F max is 120.5 MHz. So in the next we are going to see the CLK generator. This is the symbol of the CLK generator, and here we have the internal structure. No, this is a frequency divider that gives us a pulse waveform, but is not interesting. So we need a T flip-flop to obtain a square periodic waveform, because we want this a square periodic waveform. So we have to be careful with this, because this chip divides the frequency by 2. Here we have this an example of the expected time and diagram. We must obtain this from this, and the planning is this. We have the CLK generator in PLA7. All my files are here. So this is the design of the planning, and here in the development we can see the code. Let's have a look. The CLK generator is here we have the entity. It's a hierarchical structure formed by a frequency divider and a T flip-flop, and here we have all the connections. And when we simulate this in Quartus Prime, we obtain this design that is the same as this one. So we can see it's well connected. And now in the annexes we can see the test. No, here we have the CLK in, that is equal to 50 megahertz, and we can see here the output, that is 250 hertz, and we can calculate that all is okay. Here we have the period, and this is the period, and using this formula, dividing by 1 the period, we obtain the frequency. The frequency is this one, that is practically equal to this. So it's okay. Perfect. So these are my conclusions. I've learned a lot how to create a CLK generator that transforms a 50 MHz clock input to a 250 Hz one. I've learned how to create a counter modulus 24 by truncation of a counter of 16 bits, and I have deepened into gate level simulations. So that's all. Thank you very much.